Okay, let me start with a couple of quick announcements. One is that homework number 1 is due on Friday at the beginning of the class. Then there's a makeup lecture coming up on Monday, September 8th, right here in 203 McLaughlin. And then there's no lecture on the 17th and the 19th of September. I want to do a quick show of hands to see how many people are in the room that have not been able to get into the course. 1, 2, 3, 4, 5, 6, 7, 8. I was under the impression 9. I was under the impression that of the 65 students, only 4 couldn't. So that's. Is there something that I could be signing that it makes you get in, or is the course blocked? Or if you can, the 9 of you who just raised your hand, if you can come see me at the end of the class, that would be great. I'd like to get your names, and I want to pass it to Jennifer Hall to facilitate that. Are there any questions or comments before I get going? So the first homework is due on Friday. Has anybody finished it? Has anybody started it? Good, very good. Is anybody awake? Yeah. Okay, all right, everybody. Okay, so let me get going on today's lecture. So what we talked about last time was LTI systems, causality, stability, the fact that exponentials are eigenfunctions of LTI systems, and in that if they're input to an LTI system, what comes out is an exponential. If e to the j omega n goes in, what comes out is e to the j omega n, but scaled by something that's omega dependent, and that thing is the frequency response of the LTI system. And the frequency response of the LTI system, in fact, is related to the impulse response of an LTI system through what's called an impulse response. Okay? We talked about Parseval's theorem, symmetry properties of Fourier transform, and the thing I want you to remember the most about symmetry properties is that if the signal is real, then the real part of the Fourier transform is symmetric, the imaginary part is antisymmetric, the magnitude is symmetric, the phase is antisymmetric. Symmetric meaning the real part of x of omega is equal to real part of x of minus omega. That's what we mean by symmetric. So those are the symmetry properties. Then we spent a bit of time at the end of last lecture talking about convergence issues. So we talked about the fact that we have two kinds of convergence. Uniform convergence, which means that that summation of x of n to the minus j omega n has got to converge for all omega. So we play this game of I give you an epsilon, you give me an n naught. But the n naught that you give me has got to make this summation come close to x of omega for all values of omega. That's why it's called uniform. It's a much more stringent convergence condition than anything else. So the less stringent convergence condition is what's called mean square error convergence. You play the same game again. I give you an epsilon, you give me an n naught. But here, you integrate the area under the curve, the difference between x of omega and the thing the summation converges. So at some values of omega, there could be huge differences. But as long as when you integrate over the whole range of omegas, you get below epsilon, then you're all set. So that's called mean square convergence. And what we talked about was that if your signal is absolutely summable, then the summation converges. It converges to a continuous function. That gives you x of omega. And furthermore, if you plug in x of omega to the inverse Fourier transform, you get your signal back. And that's why for absolutely summable signals, Fourier transform exists. So good thing. Now, there are some signals for which Fourier transform, strictly speaking, doesn't exist in a uniform convergence sense, but it exists in a mean square convergence sense. An example of that is if you have a box-like function, a rectangular function, in the omega domain. H of omega is just a box. And if you take the inverse of that, you get sinc. A sinc function is not absolutely summable, and therefore you're not surprised that its Fourier transform is not continuous. It has a sharp discontinuity at where the box drops. However, if the sinc function is square summable, and therefore the Fourier transform of it does converge in a mean square error sense. And what that means is that again, if I play this game of epsilon and knots, any epsilon I give you, if you add sufficiently enough terms in that summation, the area between the area difference between the summation and the box function becomes arbitrarily small. Okay, so here's an example of a function that was square summable, but not absolute summable. And why did I talk about convergence? Well, because that's the main reason we deal with Z-transform. Not all signals have a Fourier transform. That doesn't mean we got to pack up and go home. There are some signals for which this Fourier transform doesn't exist, but the Z-transform does exist. So the Z-transform, which I'll introduce probably not in today's lecture, but on Fridays or possibly on Monday, allows you to define what's called a region of convergence, and therefore deal with signals that that might not have a Fourier transform but do have a Z-transform. I would like to ask for a favor from possibly 3 students. I'd like to get the lecture notes of the students who took 120 at UC Berkeley. I'd like one student who volunteered to give it to me who took it with Gaspar, one student with Joe Kahn. And is that most of the people who took 120 at one of those 2? Yeah. So the reason is I'd like to minimize overlap with 120 and sort of maximize the new information that I teach. Is there anybody who took 120 with Gaspar who can volunteer to? If you give me your lecture notes for 120, I'll have it copied, and within 7 days I'll return it to you intact. Just the lecture notes, not you? Okay. And your name is? Carson? Okay. So can you bring it maybe by Friday's lecture? Thank you. So we got one volunteer for Gaspar. Is anybody else from Joe Kahn's class in the room? Okay. And your name is? Ruth. Okay. You can bring it on Friday? Okay. I appreciate that. Any other 120 constituents here besides Gaspar and Kahn? Like Ron Fearing? No? How many other people could be from Fearing? Raise your hand. This is small enough, my eyes. Yeah. Okay, very good. So I'm going to start today's lecture. What I'm going to talk about today is sampling. A little bit of sampling, and then I'll talk about upsampling, and I'll talk about downsampling. Those are sort of the 3 main topics that I'll talk about. Now, I know that sampling, I'm 100% sure it was covered in 20 and in 120, so I will not go into the details of it very much, just as an intuitive level to refresh your mind as to what happens to the spectra when you operate on it. Just a comment. When we give the prelim exam to the first-year graduate students, one of the things we find is that while everybody knows the equations and the mathematics of things very well, they sort of lack, some of them lack the intuition of manipulating spectra and without using equations, predicting what happens to a signal so one of the things I'd like to encourage you to do in this course is when you do the problem sets or if you do exercise problems, try to solve them as much as possible in an intuitive sense. And I'm hoping that by the end of this lecture, I'll also provide some pictorial sort of intuitive sense of what happens to the signals spectra as they get sampled or upsampled or downsampled or processed or any of those things. Of course, the equations are always good to fall back on when your intuition fails, but it's always good to have some idea what's going to happen before you hit the paper and pencil and try to hit equations. Are there any questions at this point? Okay, so let me get going. We're going to talk about, if you can, great, thank you. Great. So I can talk about sampling. So what do I mean by sampling? Well, as I talked about in the first lecture, not all the signals that exist in the universe are discrete time by nature. We talked about some signals like the value of the Dow Jones Industrial at the end of each day. That's a discrete. That forms a discrete sequence, and it's by its nature it's a discrete signal. But some discrete signals have been obtained by sampling continuous time signals. And for those of you who are electrical engineers or even mechanical engineers or any kind of engineer, what are some methods that we use for sampling signals? What are some devices that we use? What are those called? A to D's, right. So how to sample, typically you use some devices that are called A to D, and they write it like that. Analog, it's called analog to digital conversion. And do we have any circuits students in this course? Has anybody ever designed or built an A to D from scratch? Nobody. Okay. Has anybody ever used an A to D in their systems? Okay, good. And so there's many principles behind A to Ds. You can, for example, have a simple voltage source, which is called VCC, and then some sort of a resistive divide all the way to the ground. And if these resistors are all equal to each other, for example, then you can compute what the voltage is at each of these nodes. And then the voltage in comes in, and you compare it to this point, this point, this point, and this point, and you figure out what range it's in, and that's how you decide which one of these values it takes. Right? So, for example, this is VCC over 5. That's 2/5 of VCC, etc. That's 3/5 of VCC. VCC is a fixed voltage, for example, 5 volts or something. So this is going to be 1 volt, 2 volts, 3 volts, 4 volts, and that's 5 volts. And you start with your signal coming in that you want to decide what it is, and you compare it to one of these, and you figure out which bin it falls in, and that's the discrete representation of your signal. It's a lot more complicated in reality. First of all, you have to, if your signal is not band limited, you have to band limit it before you feed it into an A to D, and then you have to hold it constant while this comparison is being done, etc. But what's the disadvantage of having an A to D type approach like this? What could go wrong here? Or what's so difficult about designing A to Ds in this method? For these things to be precise, for this thing to be exactly 1/5 of VCC, and this one exactly 2/5 of VCC, this one 3/5, and this one 4/5, what has to hold true? Yeah, these guys, these R's, these resistors have got to be all equal to each other. And if they're not, then this is not really 1 volt. This is 1 point something volts. Remember, A to D conversion is all about precision. Okay, and so in reality, when you design something like that, if the resistors aren't equal, then you've lost accuracy here. And what do people do to make the resistors equal? They design it, they build it, and then they take a laser trimmer and they trim the resistors manually by hand at the end to make them all equal, in some cases. Okay, if they want extreme accuracy. So when you have A to Ds, what the characteristic function you worry about is the input voltage, for example, versus the output voltage. Okay. And what you want to have is some characteristic that's as linear as possible. Essentially you have a staircase function. You're saying for these range of input, I'm just going to call the output to be 0. For these range, I'm going to call it to be this value, this value, this value, etc. Okay? And so what matters is you want this thing to be a line. You want this to be linear. And if these resistors, for example, aren't equal to each other, this thing is not going to be linear. Okay. What are some other technologies for, what are some other methods of doing analog to digital conversion? Pardon? Pipeline. Okay, and how does that work? Uh-huh. Right. So you can have successive approximation in a pipeline matter. And we'll talk about this method a little bit later. Another method is sigma delta conversion, where you actually have just a 1-bit converter, but you have feedback and you have IIR and FIR DSP type filters in order to give you the approximation of the digital value of the input. So you're using DSP itself to do the analog to digital conversion. So that's called sigma delta converters. So we'll talk about those probably in a lecture or two. Okay. But for now, what I want to talk about is what happens to the spectrum of the signal as you sample it. Okay. So the picture I want you to have in mind is you have some x sub c of t. C stands for continuous time, and t is just a real variable. And you send it to a box which converts a continuous time signal to the discrete time signal, and the sampling rate here is t, and out comes a discrete time signal x of n, which is just x sub c at times n t. Okay. So in reality, how does this C to D box work? Well, you have x sub C of t coming in, and it goes into a box here. This is the same C to D as we had up there. And you essentially are multiplying it by some other signal, S of t, which is a train of delta functions. S of t is equal to summation over n of delta of t minus nt. It's just a train of delta functions. And out comes what we call x sub s of t. It's still a function of a continuous time variable t. And then you convert this. There's a box here that converts the continuous time signal t to a discrete time signal n. So out comes x sub n. So again, I call it C to D, where it's really a conversion of between getting rid of this variable t, replacing it with this n. So the question I want to try to answer in the next few minutes, or rather just write down the answer for it rather than trying to answer it entirely, is in what way is this is a continuous time signal and it has a continuous time Fourier transform, and this is a discrete time signal and it has a discrete time Fourier transform, DTFT, the stuff we've been talking about the last 2 lectures or so. And so the thing I want to talk about in the next few minutes is in what way is this continuous time Fourier transform and this discrete time Fourier transform are related to each other. Clearly, it's got to be a function of t, which is their sampling rate. So the question is, what is the relationship between CTFT of x sub c of t and DTFT of x sub n? Okay. Well, by definition, the CTFT of x sub c of t, the continuous time Fourier transform of anything, is what? We denoted x sub c of capital omega, continuous time Fourier transform of x sub c of t. It's given by minus infinity to plus infinity, the integral from minus infinity to plus infinity of x sub c of t e to the minus j omega t dt. This is the expression for continuous time Fourier transform. Okay? And in what way? Great, thank you. And what is the expression for discrete time Fourier transform? Well, x of omega is discrete time Fourier transform of x of n, and that we've been talking quite a bit in the last few lectures. Summation over n from minus infinity to plus infinity of x of n e to the minus j omega n. Okay? And so I won't derive this relationship. I'll rely on Dan to cover it in the recitation. By the way, Dan, the first recitation lecture is today? Yesterday. Okay, it already occurred. But maybe for the next one you can show this for them. But the relationship between these two guys is as follows: x of omega is given by 1 over t, which is just a simple scaling factor, summation over k of the replica of x sub c in the following way. It's x sub c of omega minus 2 pi k over t. Okay? And it's not very difficult to derive this. The way you do it is you come back to this picture here. You start with this Fourier transform. You're multiplying it by a train of delta functions. And if you're multiplying in time domain by a train of delta function, in Fourier domain, you're doing what? Convolving with the train of delta functions, and then you relate these two things together through this relationship, and you apply the definitions, and this thing just pops right out. Okay? So I will not go over the derivation of this, but what I will do is give you an intuitive understanding of where this comes from, and then under what condition do we get aliasing and what conditions do we not get aliasing. So let me start by drawing some pictures here. And I have to be very conservative in consuming space so that all my plots fit in. Yeah, question.
Do we have to worry about taking the areas of the deltas? Because
A delta function is by definition is a function that when you integrate under it, you get 1. The area underneath any delta function is 1.
like x of n is not, they're not delta functions.
No, x of n is a discrete time sequence. It's fundamentally a different animal than a continuous time signal. This signal here, this is a train of delta functions. It's a continuous time signal. It's a function of t. And when you have any delta function in the continuous time, first of all, delta function is sort of an invention of electrical engineers. Mathematicians really don't believe in it. It's a functional rather than a function. A function is something that you give it an argument, it gives you the value. Delta function is not like that. The only thing you can say about delta function for sure is that if you integrate the area under it, you get 1. You can think of it as a rectangular box where the width gets narrower and narrower, so it's the limit of a box function as the width gets narrower and narrower, and the height gets taller and taller, such that the area underneath remains constant, i.e. 1. Or you can think of it in terms of other limiting kind of functions. But the only thing you can say about the delta function in the continuous time domain is that the area underneath it is 1. This thing is a different animal. There's no deltas here. It's a discrete time sequence which says, I give you an integer value for n, like 0, 1, 2, minus 5, minus 100, and you give me a value. This is the thing you program in your computer. If you're programming in C, it's called what? An array of 100 points or 1,000 points or a pointer. Okay? And why are we so interested in this course in processing everything in the discrete time domain is exactly because computers have provided us with a powerful way of processing these signals. Not only computers, but digital signal processors and ASICs and all kinds of devices that let you process this. Yeah?
Are we missing a block that says area of delta?
No.
No?
What do you mean, are we missing a block that says that if...
Box in there that says take the area of the delta, and then you have x of n.
That's it. I'm converting, this box is converting a signal, a continuous time signal made of deltas is turning that into x of n. And it's doing it the way you just said it, strictly speaking. But you can take the area, or you can think of it saying, like, if I have a delta function whose area is 5, corresponds to, at the particular location, that corresponds to the value of x of n being 5 at that location. Okay? I see your point of view now. Okay, so here we come some pictures of how these Fourier transforms relate to each other. First, let me do a quick show of hand, just to be sure that you guys have seen. How many people have seen this relationship before ever in their lives? Good. Okay, seems like a majority. But let me, Dan will, derive this in recitation in case you haven't. It's also, there's a nice derivation of it in Oppenheim and Schaefer. That you could easily look that up. But here we go. Here's our, let's say, x sub c of t, which is as a function of time. This is our continuous time signal. It's some signal that goes up and down like that. And it has a corresponding continuous time Fourier transform, which we call x sub c of omega as a function of omega. And for the sake of argument, let's say it's some sort of a band-limited thing, and it's band-limited to minus omega c to plus omega c. So if I've drawn the Fourier transform in a symmetric way, let's say if I'm more or less drawing the magnitude of the Fourier transform rather than the real thing. And it's because I'm drawing the magnitude in a symmetric way, this probably tells you the signal is real. But that's besides the point. Next thing we do is we're multiplying this x sub c of t, our continuous time signal, by this train of delta functions, s of t, which is a train of delta functions. So what it is let's just draw s of t. Here's our train of delta functions. They're all of equal height, which means that if I integrate the area under all of them, under each one of them, I always get 1. Okay, and it goes on. When I say it's a train, that means it goes on both ways. And this is the summation of over n of delta of t minus nt. And the distance between these guys is capital T. So 0t, 2t, 3t, 4t, etc. And then out comes how about the Fourier transform of this guy, S of t? What is it? It's also a train of delta functions, which I denote by S of capital omega as a function of omega. So this side is all going to be time, and this side is all going to be omegas. So if I were to plot that, it would be a delta here, and then another delta at 2 pi over t, another delta at 4 pi over t, another delta 6 pi over t, etc. Minus 2 pi over t, minus 4 pi over t. Okay? And now, how about x sub s of t, which is, in this picture, which is the, after I multiply my continuous time signal by this train of delta functions. When I do that, what I get is sort of a modulated train of delta functions. It's a train of delta functions whose height are no longer equal to 1. These are all equal height equal to 1. Now, when I multiply these two things together, I get, let's say this one is shorter one, then it goes shorter, then becomes taller, then it becomes shorter, becomes taller. So this is x sub s of t. Pictorially, that's really what's happening. And this one is shorter, 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 taller. So there's a sort of an envelope here that matches the envelope there, even though I'm not a very good precise artist here. I didn't draw it just correctly, but the envelope here is supposed to be the same as the envelope there. And how about the spectrum of x sub s of t? If you're multiplying two things in the time domain, you end up convolving things in the Fourier domain. So then the spectrum of this guy, x sub s of t, which is x sub s of omega, as a function of omega, is going to be this guy replicated. And let me try it now to maybe draw it maybe different from the pen. So it'll be this thing, and then 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 this thing. And I can replicate it in two different ways. I can either assume omega c was larger than 2 pi over t, or I can assume omega c was smaller, or I can assume it's dead on or whatever. And if omega c was larger than 2 pi over t, these guys would have overlapped like this, which I can draw with red. Okay, and so the red would have been is if omega c was larger than 2 pi over t. And the green is when omega c is either equal to or smaller. These guys is when omega c is equal to 2 pi over t or smaller than or equal to. So that's exactly where the Nyquist sampling theorem comes from. It's from this picture right here. In that if you have a signal that's band limited to omega c, if you want after you sample it, if you want to preserve the information that was in it, you have to satisfy this condition. Or else these things start overlapping. And what does it mean when they overlap? That means the shape of the spectra is not preserved. You get some blah like that. This part of the spectra got added to this part of the spectrum. And forever you have the sum of two numbers. And if you have the sum of two numbers, you will never know what each of those numbers were, right? If you had this on top of that, so then the value at this point is the signal here and the spectrum here and the spectrum there, and the information got lost forever. You can never recover it. Okay. On the other hand, if these guys, if this condition holds true and omega c is smaller than 2 pi over t, they just barely touch each other, so this thing doesn't spill over that. No two things get added on top of each other, and so the information is preserved. Okay? So how about x of n? Well, x of n is related to x of s of t by the relationship that this fellow here just talked about. It's really the area underneath these delta functions. So as a function of n, if I were to plot it, it's this, it takes on this value, it's still 2t, 3t, 4t, minus t, minus 2t, minus 3t, minus 4t. So it'll be this, 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 and this. So it has the same envelope as this guy did, but it's now, honest to God, it's a discrete time signal. It has indices 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. So you can now store it in a computer, process it, and do whatever you want to do. And if these, in this case, what happens to, so here I still have 0, the replication period, no matter what happens, whether they're overlapping or not, is still 2 pi over t here. 4 pi over t, 6 pi over t, minus 2 pi over t, minus 4 pi over t. They still, the replication of these greens or reds, no matter whether we're in the green case or the red case, the spectrum of this guy got repeated every 2 pi over t. Why? Because it's the convolution of this with that. And every time you convolve a train of delta functions with a spectrum, or with anything, that thing gets repeated and centered around each of these delta functions. And so what happens to little omega, which is x of omega, which is the discrete time Fourier transform of that? Well, it's all that happens, no matter whether you were in the red case or the green case, it would have been, it just gets scaled by t. So that at this point, 2 pi over t just translates into 2 pi. And 4 pi over t translates into 4 pi, minus 4 pi. So in the green case, it would do this. Oh, I didn't draw things to scale. This is 4 pi. Okay. And in the red case, the same thing. It will do this. And so, and what is, so it's just that it's a scaling factor by, so omega, capital omega turns into little omega. We go from continuous time domain into discrete time domain. It's only that this guy, whatever that was 2 pi over t, becomes 2 pi. It's just a rescaling of this axis, getting rid of all the t's. And then from this, you can go to this. And so, if I stare at this thing, does it then make sense? Does this equation then make any sense down here? Can we now say that x of omega is related to x of c in this manner? Yeah. It's the summation over k, where k ranges from, could you please roll up so people can barely see this and they can see the whole picture. Thank you. Okay, so what you can see is that, let's come back to our x of c of omega. It's our x of c of omega that got replicated infinitely many times. That's the summation over k from minus infinity to plus infinity. That's right. That's some x of c of omega minus 2 pi k. What's this thing doing? Well, this is the shifted. It's 2 pi here, 2 pi here. It's just telling you that this thing is periodic and it's repeated with period 2 pi everywhere. And what's this scaling by t is telling you? It's the same scaling by t that I just talked about, going from here to there. So what it's telling you is that x of omega is the scale factor summed over infinity, which is the repetition, omega minus 2 pi k, that's the 2 pi repetitions. Remember, the k is the index here, and then the t is the scaling factor. Okay? So if I had so the bottom line, the thing I want you to walk away with this is, if right, actually there's a little typo here, and none of you caught me. Is this omega c larger than 2 pi over t that causes no aliasing? And that causes aliasing or something else. This is 0. This is 2 pi over t. What's this point here? Pi over t. And so in the green case, what's this frequency? That's also omega c, right? So if I want no aliasing to happen, omega c has to be smaller than what? Pi over t, not 2 pi over t. So I caught my own mistake. So this is pi over t. and this is pi over t. So let me, is that obvious? So let me blow this guy up here, down here. So what I'm saying here is that these guys are repeating themselves, and this is 0, this is 2 pi over t, and the middle point is pi over t. So if omega c, this guy, is just equal to pi over t, they barely touch each other and they don't overlap. So if omega c is smaller than pi over t, then we get no aliasing, and we can recover the signal. Then it's possible to recover x of omega exactly from x of omega, from the discrete time Fourier transform. You can recover the continuous time signal from the discrete time signal. That means the sampling process didn't make you lose any information. It's all there. It can all be reconstructed. So that's called the Nyquist sampling theorem, or Shannon sampling theorem, or there's also a Russian guy who has a claim to this. I can't remember now. If you talk to people of Russian descent, do we have anybody Russian here, of Russian descent? They'll tell you immediately there's a Russian guy who also invented it simultaneously with Nyquist and Shannon. So that's really what makes you preserve the information. Now, let's talk about real life just a little bit before we move on to upsampling and downsampling. In real life, do you know which kind of signals are you aware of that are band limited? Human voice. Is it band limited? And to what frequency, if it is, to what frequency is it band limited? Anybody? 22 kilohertz, you're saying. And that's a different thing. You have to understand. What your ears can hear, I'm sounding like Dr. Seuss now. What your ears can hear is different from what your voice can produce. Your ears can have a much higher frequency range. We can supposedly hear up to 30 kilohertz, but producing 22 kilohertz, no, I don't think, no. I don't. Pardon? 3 kilohertz? How many people think that human voice is band limited to about 3 kilohertz? Any other votes or ideas? Yeah. I'm surprised none of you is asking a key question. Instead of answering my question, you should have asked a question from me. Right. Who said that? It's correct. Male or female. Right. Whoever who said it, correct. Male or female. So who has higher frequency, male or female? Right. Right. Male who?
I mean, in the ancient opera world, they used to castrate males and then they could...
Oh, boy. You know, I learned something new. I taught this course for 15 years. I never got that answer. But okay. No, the females have higher frequencies, and the answer for 3 kilohertz is perhaps accurate. I mean, the truth of the matter is you can chop off anybody's voice to any frequency and then have an approximate reconstruction of that voice. So, for example, I think what that fellow over there who said 3 kilohertz really meant was when you use the landline telephone lines, their bandwidth is about 3 kilohertz. So whether or not your voice is band limited to 3 kilohertz or not, that's what they chop it off to. And so the point I'm trying to arrive at is that no signal in real world is truly does that as a function of frequency. It's truly band limited. Most signals have sort of a decay, and this thing goes on and on and on. I mean, you could say, well, most of the energy is contained. It becomes an arbitrary thing as to how much you want to sample it. You can say, okay, I'll sample it all the way here. And then somebody comes around and says, no, I really want to listen to all the frequencies that the Beatles have to produce. I want to sample it to here. And then someone said, no, what's this generation? What do you guys listen to? Like Eminem or what's the thing? I mean, Britney Spears? No. That's not it. That can't be. That's my son's generation. Anyway, whatever. Lizzie McGuire, is she a singer? Anyway, whatever. You could say here or here, it goes on, You could say, I really want to have a faithful reproduction, so I'll go. Or if it is classical, you could say, well, that's good enough, you chop it up, for example. So the answer is, in real life, signals are approximately band limited to a certain thing. But nothing is ever entirely, truly 100% band limited. The notion of band limitedness is a mathematical invention of our mind in order to be able to process things. And so the more of the spectra you keep, the more faithful representation you have. I mean, as an example, on your cell phones, the effective bandwidth you're getting out of your voice is not even 3 kilohertz. It's more like 2 kilohertz. When the channel becomes bad, the sampling goes down, and that's why you have so much distortion, right? So the bottom line is you can make any signal to be any band limitedness that you want, as long as before you start sampling it, you band limit it. In any A to D system, as I said at the beginning of the class, before you start doing any sampling, people realize that no signal is ever band limited. Even if it was band limited by nature, it has noise added on top of it. They always filter it, get rid of all the higher order frequencies, and then they start sampling it in order to avoid all kinds of aliasing, all kinds of other sort of bad things that happens. Okay. Any questions on this sampling stuff? All right. Let's move on to downsampling and upsampling, which are sort of the next topics I was going to cover. So let's talk about. Actually, one last comment about this. I sort of want to make this thing. Do you know of a commercial entertainment type piece of electronics that has a sampling rate that you're all aware of? Like, what sampling rate your CD player uses? Right, 44 kilohertz. So that's a known sampling rate that all the audio CD players play. And what? And one other question: do you know the sampling rate that's used in cell phone industry? For example, the GSM/GPRS portion of cell phone industry uses audio coding techniques that's called AMR. And I'm afraid I don't really remember what the acronyms stand for. But do you know what bit rate they use? What sampling rate they use? Right. It's roughly 8 kilohertz. So they're roughly, they're trying to produce sort of 4 kilohertz type version of things. And if the going gets really tough, then if the channel becomes bad and the signal is not getting through, then they lower the sampling rate and they lower the bit rate and they adapt to the condition of the channel. Just wanted you to have some data points of in real life what are some typical sampling rates people use. Okay, so let's talk about downsampling. So what does downsampling first mean, and why do we care about it? Let me just tell you what it is, and then see if you can guess as to why it's of any use. I have a signal X of n. It's a discrete time signal. It takes on values like this. It takes on the heights values A, B, C, D, E, F, G, H, I, etc. And when I downsample it, what I mean by downsampling it is I want to retain, I get a discrete time signal here, and it keeps on the value A here, but the value, you throw away B and you keep C, throw away D and keep E, throw away F and you keep G, throw away H and you keep I. Okay, so downsampling means you get rid of In this case, I've gotten rid of half the samples. I could that means I've downsampled by a factor of 2. I could downsample by a factor of 3, which means that I keep 1, throw away 2, keep 1, throw away 2, keep on doing that, right? So this is downsample by 2, by a factor of 2. And sometimes they denote that with an arrow and a 2. That's sort of the mark for it. So can anybody guess why people would want to downsample anything? What's some application? What would be some motivation for downsampling? Increased speed of what? Or in other words, decrease the storage amount. That's exactly right. You want to decrease the number of samples that's needed to represent something, an image or a signal or a voice or an audio. And you're doing that, by the way, at the expense of what? At the expense of only having this much of the spectrum instead of this much, for example. Or some we'll talk about what happens to the spectrum in just a second. But one big motivation for downsampling is just to have fewer samples because, I don't know, your disk got filled up. That's not a very good argument because disks are so cheap nowadays, and they're getting cheaper progressively. They're almost like commodities. But what's not a commodity is, let's say, the storage on your cell phone. Like if you have a Nokia phone like I do from like 4 years ago, the amount of memory that phone has is less than 100 kilobytes. So those of you I think you guys are way, way too young to even remember. I don't think PCs ever had storage of less than 100 kilobytes, ever. So it has nothing to do with you being young or old or remember or not remember, none of that. So your phone can only store so many applications, so many videos, so many audios, so much information. Why? Because it's a portable device. The disk on this computer here, like it's cheap. It's what is it? It's $100 per gigabytes now almost, right? Why is it so cheap? Well, because there was a lot of competition that drove the price down. But more importantly, it's not a portable thing. It's hooked up to power. It chews up a lot of power, and it's big. And it weighs a lot. You can't carry it in your purse or in your pocket. But your cell phone, you could, and that's where the storage becomes an issue. So anyway, downsampling by a factor of 2. So the question that I want to try to address is the following. If I had so intuitively what we've done here, we're just keeping one sample and throwing away n, where in this case it was n equal 2. So this is called downsampling by a factor of n. So more general than that, what does it mean for me to downsample? And do I lose any information if I downsample? I certainly do, but whether or not it's detrimental or not, it depends on a lot of factors, which I'll talk about right now. So if I had started off with a continuous time signal x sub c of t, continuous time signal, and suppose I sample it at 2 rates. Case 1, I sample it at rate t, and what I get is x of n is equal to x sub c of nt. This is my discrete time signal, and this x sub c, again, c stands for continuous time. Okay, and then the other one is I sample it, this is rate 1. This one I sample it at a different rate, x sub c of t. I pass it into a C to D device, continuous to discrete time device, and I sample it at rate capital MT. So I'm sampling it at this, M is an integer, like 5. I'm sampling it at 5t, for example, or 10t. That means that I'm sampling it 5 times slower. And I get a new signal, I call that x sub d of n. Well, this thing is the same as x sub c of n. Instead of t, it's now mt. Okay? So now x sub d, in some sense, is the downsampled version of x of n by a factor of n. So x sub d of n is downsampled version of x of n by a factor of m. And the thing I want to try to figure out is what's the relationship between discrete time Fourier transform of this signal and discrete time Fourier transform of this signal. So I want to relate dTft of x of n to dTft of x sub d of n. How are they related to each other? So pictorially what I have is a picture like this. is I have a continuous time signal doing its thing, and the first time over I sample it at rate t, so I get these samples. And the second time over, let's say m is 2. I'm subsampling. I decide to sample it by 2t. Okay, that means I keep this one, 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 etc. And so in this case, the distance between these two guys is 2t. Okay. So how do I find out how do I relate these two DFTs? Well, I write down the expression for each of them, and then I invoke the only thing that I know about it, which is this relationship. And let's see if we do that, what do we end up getting? Well, we start with x of omega, which is just the DTFT. I'm sorry, x sub d of omega, which is just the DTFT of x sub d of n. Well, and the way we're going to do this is through this signal, the continuous time signal, x sub c of t. Okay? Based on what we covered in today's lecture, i.e. this equation here, I have a continuous time signal, and how do I get x sub d of n? Well, all I'm doing is I'm sampling it at rate n times mt. Okay? Actually, hold on, let me backtrack. Let's remove the d's for a second. Let's start with the easier case instead of the harder case. Let's just talk about x of omega. Okay? You have x of c, you sample it at every t seconds, you get x of n. And how is the x of omega, how is the discrete time Fourier transform here related to the continuous time Fourier transform? Well, it's exactly this relationship that we had written a second ago. So it's 1 over t summation k from minus infinity to plus infinity x sub c of omega t minus 2 pi k over t. Okay? That's just looking at this signal, sampling it, and this is how the continuous time Fourier transform is related to the discrete time Fourier transform. And what can we say about now x sub d of omega, now the harder one, which is dtft of x sub d of n? Well, it's the same thing, the same relationship as we had before, except that now we're sampling at mt instead of t, so you have to replace everywhere you see a capital T, you replace it with mt. So it's 1 over mt, okay, summation, and to avoid future confusion, and I see the next steps, but you don't, but I'm just going to change the dummy index k to r. R from minus infinity to plus infinity, x sub c, omega, now replace the t with mt, okay, minus 2 pi, k is the same as r, our dummy variable, over, replace t with mt. So that's how the continuous time signal is related to x sub d. Yeah.
Is that omega over mt or just omega? Because dimensionally they don't match. Omega is.
Do you believe in this?
Um,
I just separated omega t minus 2 pi k over t.
Omega is in radians. How does what is omega? Is it frequency? Or because if it's frequency, then it's radians per second, right?
Mm-hmm.
And you're comparing an angle with a frequency. You're putting the same thing together.
No, this omega is the discrete time frequency. It's not my notation. Just to go back to this thing. Where's page 2? I'll show it to you. No, the first where they did all my drawings here. In the continuous time domain, I use capital omega. Right? The little omega here is for the discrete time domain. Did you get it? Now the units match up? Okay. What I think part of the problem I always find is that I really wish that for 120 people would have used Oppenheim and Schaefer or Oppenheim and Wilsky or some derivative of that, because then you shouldn't underestimate the power of notation. You can really trip people up by changing notations on them. It's the same thing, but if you just change little omega with something that you always used to seeing at big omega, it gets to be confusing. Okay. Is that clear to everyone? So all I did is I went to this thing, and I exploited this this relationship that related the continuous time to discrete time type things. Now I'm going to do a change of variable, which is one of the things you do quite a bit in this business when you're dealing with discrete summations and all. Okay, I'm going to say R is equal to I plus K times M, where K ranges from plus infinity to minus infinity, and I ranges from m minus 1 to 0. So what do I mean by that in particular? Well, what I mean is, or why can I even do that? Well, so when k is equal to 0 and I ranges from 0 to m minus 1, I end up getting R ranging from 0 to m minus 1. When k is equal to 1, and again I ranges from 0 to m minus 1, then R ends up being ranging from m to 2m minus 1. And then when k is equal to 2, and I ranges from 0 to m minus 1, R ranges from 2m to 3m minus 1. So effectively what I have by this change of variable, what I'm doing is, if this is the R line, okay, so I go from 0 to m to 2m and 3m, this and minus m, minus 2m, minus 3m. So this range here corresponds to k equals 0. This range here corresponds to k equals 1, k equals 2. And this range k equals minus 1, k equals minus 2. So instead of letting R go from 1, 2, 3, 4, 5, 6, 7, 8, I'm just letting, again, k go from 0, 1, 2, minus 1, minus 2, but then let I cover the m values here, and the m values here, and the m values here. Okay, it's merely a change of variable, merely a mathematical thing. And if I do that, well, what do I end up getting? I'm going to fold this so you can continue to see this guy. So what do I end up getting if I do this change of variable? Well, what I get is x sub d of omega, which is the same thing as I had there. It's 1 over m, which is the thing I had here. And now I'm going to have two summation. A summation from I equals 0 to m minus 1. And then I have 1 over t inside here. It doesn't really matter. 1 over mt, I've split it up. And then now I have a summation for k. Remember, I was ranging from 0 to m minus 1. And now I have my summation for k ranging from minus infinity to plus infinity of x sub c of the same things that I had back there. Omega over mt minus, now I have 2 pi r over mt, and r is I plus km. So I replace the r here with I plus km, and I get 2 pi 2 pi k over t minus 2 pi I over mt. Okay? So I put km here, the m's cancel, I get 2 pi k over t, and then I put I here, 2 pi I over mt. That's it. That's what this change of variable does. And how do I know why I do that change of variable? Well, because I've already seen this a million times. I wasn't the first one who invented this anyway. The person who did that was a genius and deserves all the credit. But the more of these things you do, the bag of tricks become standardized, and you'll see that the same things sort of keep repeating themselves. So that's our x of d. And next thing I want to do is rewrite that. X of d of omega is 1 over m summation I equals 0 to capital M minus 1 of 1 over t of summation k minus infinity to plus infinity of x of c. And now I'm going to combine this guy and that guy, omega minus 2 pi I over mt minus 2 pi k over t. Okay? And now what can I say to this summation down here? What is this thing? Remember this. That's a good thing you don't write on the board. You can fold papers. Compare this expression to this expression. Or, yeah. What can we say about this expression here? Well, this is x of, it's 1 over t, it's summation over k, that's the same. X of c, it's the same. Something minus 2 pi k over t. Here I have omega over t minus 2 pi k over t. So all that has happened is what? That's right. So it's just x of omega, little omega, except that I'm replacing omega with something else. Little omega, I'm replacing it with omega minus 2 pi I over m. That's all there is. So looking at that and looking at this other thing, this thing that I have in accolade here is x sub omega, where omega is replaced with, I put an arrow, with omega minus 2 pi I over m. In other words, this is the same as x of omega minus 2 pi I over m. Well, this x is the dTFT. Okay? It's straightforward manipulation of symbols and equations. Nothing more to it. But when we're done with that, then we're going to draw the pictures, and then you get the intuition. And from then on, you can live with the picture and not have to deal with equations anymore. So what that means here is x sub d of omega is 1 over m summation from I equals 0 to m minus 1 of capital X of omega minus 2 pi I over m, which is exactly what I was going to find out. I was going to relate, my goal was relate the dTFT of x of n to dTFT of x of d of n. That was my goal. This is the dTFT of x of n. This is the dTFT of x of d of n. Remember, this was our picture. This was the beginning of our problem. We sampled a continuous time signal at rate t, we got x of n, but then we sampled it at rate mt, which was quite a bit slower, and we got x of d. D stands for down sample, in case you're wondering what D stands for. And I wanted to relate these two dTFTs, the dTFT of these two guys together, and boom, here it is. Okay, so this is the relationship between the dTFT of x of n and xd of n. This is it. And if I, just for the sake of simplicity, for drawing diagrams, let m equals 2. I want to have, I'm subsampling by a factor of 2. I can do it by any factor, any integer factor, 3, 4, 5. And what I get is x sub d of omega is equal to 1/2 summation I equals 0 2 minus 1 is 1, of x of omega over 2 minus 2 pi I over 2. And if I do that, then let's simplify that. I can, it's just two terms in this summation, so I get x of b of omega is equal to 1/2 of x of omega over 2 plus x of omega over 2 minus pi. Okay? And let's see if I can show some pictures here. Yeah. But before I do pictures on Oppenheimer and Schaefer, so let's draw some spectrum here. Okay? So suppose I started off with some x of omega that looked like this. As a function of omega, I had, this is 0, pi, 2 pi, 3 pi, 4 pi, and suppose I had an x of omega that went like this, went all the way to pi over 2. Okay? And, well, the same thing here, did this, and the same thing here, and it did that. Okay? And now I'm trying to plot, this is my x of omega. Now I'm trying to plot x of, sorry. X of omega over 2. How would x of omega over 2 look like? Because I want to plot that. Here's my omega. How would x of omega over 2 look like? Pardon? Yeah, it's like getting this and stretching it this way. Stretching it this way by a factor of 2. So it would start here, but if this is pi again, 2 pi, 3 pi, and my 4 pi, and 0, this thing will go like boom. And this guy will go like, it gets stretched. That's what scaling by factor of 2 to your horizontal axis does. It pulls it like that, like a rubber band. And the next term I have to do is x of omega over 2 minus pi. So how does that look as a function of omega? Let's plot that. So this is omega. So I'm trying to x of omega over 2 minus pi. And what does that do? How does that spectrum? And why do I need that? Because of this term here. What would that spectrum look like? Ooh, I made a mistake. Nobody caught me. Is this x of omega over 2? No. I'm glad you... Sorry, just throw that away. Let's start. Sorry. So I quickly draw it again. X of omega, that's 0, pi, 2 pi, 3 pi, 4 pi, and it went all the way to pi over 2, and here it went over pi over 2, and here it went over pi over 2. So let's draw, as a function of omega, x of omega over 2. And it's like stretching it, so it's like stretching this axis, okay? So whatever that was at pi over 2 comes to pi. But this one also shifts to 4 pi, okay? So then there's nothing until 4 pi, and that thing is this guy doing this, okay? So this is x of omega over 2. Is that why you guys raised your hands? Thanks. Okay, is it clear to everyone why this is x of omega over 2? It's this axis just getting scaled by a factor of 2. So whatever that, it's almost, if you forget how to do it, just go here and cross this out and make this pi, make this 2 pi, make this 4 pi, make this 6 pi, and make this 8 pi. That's all that means, scaling by a factor of 2. Right? multiplying the labels here by 2. And then the next plot I want to do as a function of omega is x of omega minus 2 pi, no, omega over 2 minus pi. And what's that? It's the same as this thing, but shifting everything just by pi to the right. So what happens is this guy just gets shifted by pi and comes here. Or rather, this is x of omega minus 2 pi over 2, so everything gets shifted by 2 pi. So it will look something like this. And then the other ones, the other replica, this thing got moved here, this thing got moved way to that side, and there's some other stuff at this end that's not visible, but this goes from pi to 3 pi. And why am I interested with x of omega minus 2 pi over 2? Because of this. This is x of omega minus 2 pi, the whole thing over 2, and this is x of omega minus 2 pi over 2. These two things are the same. Okay? So now, what this is telling me is that x sub d of omega is this plus that times half. So it's this signal plus this signal times half. And what is that? And the function of omega, well, this plus that, there's this guy, and then there's this guy, and there's this guy. So pi, 2 pi, 3 pi, 4 pi, 0. So this is x sub d of omega. And what can we say about this? What's the most, can you zoom out just a tiny bit so people can see the labels and everything? Great, thank you. Including that. So if I look at this whole picture, this is my x of omega. This is what x of omega over 2, which is this term, looked like. This is the second term, x of omega minus 2 pi over 2, looked like. And this is the, so if I started with a discrete time signal with this kind of a spectra, after I downsampled, I get that. Now, what's the immediate observation comes to your mind? What can you tell me? Yeah, and please use the mic if you can. Thanks.
Maybe the same thing will happen if m is more than 2.
Yeah, but I mean, looking at this picture, what could potentially worry you? Not that I want you to be a worrisome kind of person, but yeah, is that, look, I first scaled these by a factor of 2, then I pushed it, and then I'm adding it. What could potentially bother you is that if this thing miraculously didn't go to pi over 2, suppose it was a little bit fatter, like it spilled over somewhere here, then this thing would have spilled over somewhere here. That's still not a big deal. But then when I shifted it by 2 pi, when I came to this signal and I shifted it to 2 pi, if let me just draw it with green. So if this guy was doing this, went all the way to there, then let's say we went to 3 pi over 4, right? Now, if in this picture, this would have gone to here, for example, and this would have gone to here, this would have gone to here, this would have gone to there, this would have gone to here, this would have gone to there. And this picture, then, this is just a shifted version of that. This would have gone to there, and this would have gone to there. And then when I added these green things here, on top of these green things here, they would have overlapped again. And then, in that case, the spectra of x sub d of omega, the downsampled one, could not have been used to precisely recover x of omega. And intuitively, what does that mean, or what is that telling you? Is that if your signal didn't have capacity or room to be downsampled, here we were lucky. There was plenty of room between this point and that point. It was oversampled in some way, right? It wasn't critically sampled. Critically sampled means when these things are touching each other. If x of omega was critically sampled, then downsampling it would make you lose information. Will give you an x sub d of omega that would make you unable to recover x of omega from it. And does that make any sense? Yeah. If you just critically sample something, if you just sample something at the bare minimum so that it's barely non-aliased, now start with that and downsample it by a factor of 2, you're definitely going to alias it, right? Because to begin with, it was just barely not aliasing. So this confirms all of the intuition that you've accumulated in the course, which is, because this x of omega to begin with was oversampled in some sense, it only went all the way to pi over 2 instead of to pi where these things were touching. And because it was oversampled by a factor of 2, downsampling it by a factor of 2 didn't mess it up. It allowed you to just make the x sub d of omega just barely touch each other and not have aliasing. But if this guy was a little bit less oversampled, it was a little bit fatter here, then you would have had aliasing. So the thing I want you to walk away is, downsampling, if you're not careful, is a process that could make you lose information. If I start with a song and I downsampling, if the song was critically sampled, if it was not oversampled by anything, downsampling it will make it sound worse. It'll cause aliasing. That's why people, before they downsample, what do? They always band limit the thing. They always low-pass filter it or band limit it to make sure that these things don't get spilled over. A criteria for any time you do downsampling, just before you do that, because you're not sure whether you were critically sampled or not critically sampled, if you were not critically sampled, the low-pass filtering doesn't harm you anyway. But if you were spilling over here and you weren't ready to be subsampled, by just low-pass filtering it, you chop this guy off, chop this guy off, chop this guy off, and therefore you prevent further aliasing. Okay? All right, I think I'm going to stop the lecture right now. See you on Friday. Yeah.
I mean, if you band limit it, does that mean that you guarantee